Hi, everyone. It's always the first talk and the last talk of the day are the more difficult one. Haven't gotten awake yet, or the other way around. And so I changed a little bit the title of my talk. Initially, I was planning to talk about something else, Schrödinger bridges, which I have given already a couple of lectures. So I decided to talk to you about some very recent work on the Sub-Riemannian structure of optimal transport. Most of the talk is on classical optimal transport and a little bit at the end on quantum. And this is work that is currently also ongoing and connects to some very interesting concepts in physics. So this is work with Mahmoud Abdelgalil, a former student at UCI and currently at University of California, San Diego. So we're all familiar with the optimal transport problem, which originally was posed by Gaspar Monge many years ago to move a mass from one position to another, redistribute the mass according to some specifications. And of course, this has given a very fruitful direction that has touched almost every subject in science. And I here have some of the names of people who have been responsible for great strides after the 1990s. It has impacted optimization, probability theory, PDEs, analysis, and so forth, and I probably shouldn't belabor this in this audience. In modern day, sort of the whole thing is spurred by applications. Of course, here we're looking at non-commutative transport, but we shouldn't forget where this came from and why we are all sort of immersed in this subject. The first application started sort of in physics. Of course, there was also in economics and so forth, and then computer imaging, machine learning was a big sort of customer, then network science, biology, and so forth. And I put lastly thermodynamics, and this is extremely important because some of the early contributions by Otto Kindler and Jordan showing gradient flows, it couples very much optimal transport with dissipation and heat. And again, we will be playing throughout the quarter with quantum versions of that. Now, the important thing of that is that normally, when you talk about transport, what comes to mind is you move one distribution to another, whereas here we started sort of focusing more and more on the idea of having cycles. So you move mass around, how? Under some action of some potentials. So you think of them as particles that are distributed, and then you have the potential which moves like an accordion, pushes in and out. And you allow exchange energy, work, and so on and so forth. So this kind of set the stage of trying to look at it from a slightly different angle. So a few slides about the classical, and then I'll come back to the motivation. I'll go very quickly. Optimal transport maps, map X to some var phi, minimizing a certain cost. Throughout, we are concerned about the quadratic costs, and you need to match the masses. Of course, everyone in this audience, we're familiar with dynamic formulation that sort of launched this kind of new phase of development, the Benabou-Brégnier formulation, where you look at the Wasserstein distance between densities. Here, I have to apologize, I'll use rho and rows for density matrices, probabilities, and sometimes I'll switch to mu because the slides were not kind of uniform. So the Wasserstein metric is the infimum over rows and velocity fields that minimize this action integral. So you integrate over all particles their kinetic energy, and you integrate from beginning to end of the path. So, and the important sort of conclusion out of these investigations was that the optimal transportation vector field is the gradient of a potential. it's in some ways the most economical because it's irrotational. You don't have curl. Hand in hand with this comes the Riemannian geometry of Otto that is gained by the framework and can be placed on this, the space of probability densities or probability laws. So here you can view rho as a positive definite density function, for example, that integrates to 1. The tangent space, the perturbations of rho that retain this property, they have to integrate to 0. So intuitively, such perturbations form the tangent space. So the interesting way of looking at it is that instead of putting the metric directly on the deltas, then you correspond to that a vector field that infinitesimally will move you in that direction. And that vector field can be computed by solving the Poisson equation. So you take the delta and the phi, these are both functions. The gradient phi gives you incrementally sort of the optimal direction to go so that you produce this perturbation. So this is nothing but the continuity equation. And then the Riemannian structure, and then we're going to see it in various forms, is you locally around the point rho that you are on the space, the inner product between elements of the tangent space is defined to be this, which is echoes the concept of kinetic energy. And then you can show that the geodesic distance between 2 points is actually the infimum of along the paths that minimizes this the length. And this is the Riemannian distance. So what we're going to do today is the following. So we're looking at curves in Wasserstein space with this matrix and all of that. This is a path of an ensemble. But what the difference here is we're going to think of not just the distribution, but we think of the ensemble as consisting of particles that are distinguishable. It's not just the density at the beginning and at the end, but where actually did the particles go. We want to track them. We want to see where they went. So the particles obey individually a differential equation of this sort. Here you have some potential, it's the gradient of a potential. If we're looking, most of the talk will be about quadratic potentials, and then basically you have as your control to steer them a matrix A which is symmetric because the gradient of the potential. So you can think of the potential sensed by all the particles. You know, you squeeze them, you push them around, and they move, but you have more ability to steer them.
Tryphon?
Yes.
Have the rows from the previous slide been promoted to fees on this slide?
Sorry, what's that?
The rows, are they fees now?
The rows are P's.
Or you had the flow of row T's? And
right. Let me see here. Where are the P's?
Phi, there are phi T's sensed by all particles.
No, phi is the same as before. It's the same phi as before. Is the velocity.
Sorry, which one?
The phi.
Phi.
The phi. Oh, no. Okay, phi is the potential. And throughout, I'm going to use phi for the potential. But the transportation map will be either var phi or capital phi. So those things are connected, okay? So here, for example, this is a var phi. It's a transportation map. Right, and I had it before. What did I have it? I forget. Yes, here, var phi, the transportation map. Okay, so I'll try to keep them again. The potential and there is a same symbol, but somehow it will be different. Okay. So the first part of the talk, we'll be talking about the gradient of a potential, how you can steer distinguishable particles. And the second will be kind of along the same spirit when the control action, which is the A matrix here, is partially constrained in some directions. So this, for control purposes, is very useful to think that you have a drift which you cannot do anything about, and then you have certain directions that you can regulate. So this is a very, very important for various reasons. And both of those, you can think of them as a control problem to steer the particles, either by a gradient of potential or by a feedback gain, which is broadcast to all the particles and everybody's using it, okay? So, I try to reposition people in this room and I give you some instruction, go from here to there. But I have to send you a message that you can all interpret it and you interpret according to where you are. In other words, I'm not going individual to tell you, you go there, etc., right? I'm going to collectively steer an ensemble. So we will see that you can do a lot more. You can do as much if you have some constraints. And then I'll explain also why this is also important in the context of quantum. So the Sub-Riemannian structure we're trying to understand is trying to resolve internal degrees of freedom and subject to curves ensuring terminal configuration. So in other words, you want to tell the particles where they're going to go or to see how much control you have. So the first, let's begin with the control being a gradient of the potential. Now, so this is standard optimal transport with discrete masses. So you have those two, and you try to reposition them in the positions of the blue distribution. So if you think about this, the distance between this dot and that dot is too huge. So if you square it, it's too big. The optimal transportation plan swaps the position of the particles. So if you try to move them now from the blue to the red, again they swap, and then again they swap. So if you go around the cycle, you have a permutation. This is not surprising. Yes, go ahead.
Kind of stress that the particles are distinguishable.
Sorry?
On the last slide, you stress that the particles are distinguishable, but now it seems like it's not important who goes where.
No. So right.
But it was important for you on the other slide, so I'm trying to understand.
Okay, no. So the important thing is here that we look at the particles individually. So by all of this analysis means that this guy has a label. So it goes here, there, and then we realize that after we went through this process, we repositioned the mass exactly where it was, but individually the particles are not in their starting position. They were swapped. And we're interested in knowing exactly what is going on, and can we just recycle so that they get back to their original positions. So if I tell, let's say, 10 people from this room, you get up and move to those seats as fast as you can, and then give a command to go to another set of seats, and then return back. You're not going to get to your original seats. And this is no surprise, because the Monge map, right, is basically a symmetric matrix here. If you compose three symmetric matrices that, and the outcome is that the terminal distribution is equal to the identical, the starting one, you're going to get some sort of rotation. You're not going to get the identity. Symmetric matrices, when you multiply to symmetric matrices, you don't get symmetric matrices. So for example, the optimal transportation map, we're going to see more on this, right? So this is, again, I don't want to belabor the point, this is a transport of Gaussians. So these ovals represent equiprobability circles. So you have, if you start with, let's say, the red, you have a particle here, and you have the Monge map will bring it here, then it will swap it to this position and then back again. So you affected basically a rotation. And you can think of that. Think that you have a piece of dough, okay? And you put a marker on it. Now you squash it. Then you squash it this way, and you squash it that way. And then you bring it back to the original shape. The marker that you put is not going to be where you started. It will rotate. I think as kids, we all played with that, okay? So this is, so here again, some formulas. I should go quickly through this. Let me see, it goes until, yes. So we're going to be dealing with centered Gaussians. Sigma would denote the covariance. We identify the Gaussians with their covariances, and we transport under a gradient flow. So this A is symmetric. Var phi tells you where the particle is transported. And because we are in this Gaussian linear setting, linear dynamical equations, the diffeomorphism that is affected by the var phi is basically linear, and this matrix phi, capital Phi, is what is called the state transition matrix, and is the solution of this matrix differential equation, initialize the identity. And this is basically the time index integral of this time varying A's, okay? So when we are transporting between normal distributions, the transportation cost can be written in a variety of ways. It can be written as the minimum of a coupling between beginning and end of two random variables that are distributed according to the two Gaussians. The optimal transportation plan sits on the trace, the support of this transportation map. This means push forward of the mu. The optimal from beginning when transportation phi can be written, can be given an expression that depends only on the marginals, and the distance can be given by some expression like that, where these are covariances. Then the transport, if you are interested, what happens from the start to the end, they follow Macan geodesics. So individual particles are transported by this phi, can be given a closed form expression like this. And this is the density with the sigmas, sigma sub t. Now the sigma sub t can be thought of as the covariance of the particles at time t. You can have an expression like that. It's the push forward. By this here, when these are covariances, I will mean the congruence transformation. You take the sigma and you sandwich within the phi and phi transpose. Alternatively, the covariances obey this equation, which is called the Lyapunov equation. And the thing is that, right, the A needs to be symmetric. So for example, one can ask the question, I give you a starting sigma 0 and a terminal sigma 1, find the optimal protocol directly from that. How do I steer from one end to the other, subject to whatever optimality condition you want? The issue of controllability here is also interesting, like can you go from any point to any other point, short paths and so forth. Now, at the level of the individual particles, we have to pay attention to this equation, because this tells us what happens internally. So this is linear diffeomorphism of the plane. Again, just very quickly, the Wasserstein triangle that I showed you before, you can write down explicitly what happens to the covariances of the various distributions, right? And basically, it's a composition of these three Monge maps. And the composition of those, you go from 1 to 2, from 2 to 3, 3 to 1, you end up with a an element of the special orthogonal group, okay, which preserves the sigma. So in other words, theta, sigma, theta transpose gives you sigma, right? So this is a notation, okay? So in other words, this matrix is orthogonal. Again, the internal degrees of freedom, keeping track of what happens to every particle. So these are the questions we're interested. Is it possible to realize any holonomy, any rotation of what, the internal distribution of the particles by a choice of A? How you can construct optimal curves that affect such a rotation. And basically all of this comes from viewing the Wasserstein metric on the base space of densities as a submersion of a much larger space which looks at the internal structure. And this goes back actually to the work of Otto. So the way to think about this is you have to think of here is a base space. We identify densities with their covariances. So every point is a symmetric n-by-n matrix corresponding to a Gaussian. Above it, there's a fiber of factors. And the factors are related by saying simply that sigma is equal phi transpose. And this is, of course, non-unique, is unique modulo some orthogonal matrix on the right. Occasionally, it's important to have a reference matrix in the middle. And this is what is all this extra thing is, that sometimes you have a reference covariance. For example, you could take this to be the identity. If this is the identity, then one of the factors is the identity, and there are others. And this would be just the special orthogonal group. And likewise, here you're going to have the factors. So the base space is the GLN, the general linear group that sits above here. The fibers are inside the general linear group, and they're sitting on top of the sigmas. Is this clear, right?
Is GL plus the connected component of identity?
S, yes, S is the connected component of the identity. Yeah, because we can't go outside, this is, yes. So, and this is again the same point I made before. So you have a Wasserstein triangle. So you have, let's say, some point here. And if you try to follow Macan geodesics, you go from here to here, from here to here, and from here to here. But if you are up on the principal bundle on the general linear group, these are the factors. So you go from here to there, from here to there. When you return, there is a holonomy. Okay. Now you could choose to not go following a Macan geodesic, but to go along a longer path so that it brings you back to the beginning, which means repositions the particle exactly how they started. So this is the bundle from GLN to the symmetric. And the plus is the connected component to the
You're not restricted to triangles.
Sorry?
You don't only consider triangles, so you consider any side.
We will consider more. I mean, yes, we can consider more general curves. Okay. So now, in trying to do geometry up there, you need to decide what is parallel transport, what is allowable, what's not allowable. And of course, we know what's allowable are the directions that A is symmetric. So we're going to have a transition between successive from the position which you ended up by doing this to the new position, it's infinitesimally a Monge map. Now, so the directions that you are allowed constitutes what's called the horizontal space, and there's a vertical space, and the vertical space are velocity fields in the tangent space of the general linear group. The plus here means that it has a positive determinant, okay? So that they are in the kernel of the bundle structure. Right? So this is what's known as a principal-Erdmann connection, and it has to do with the choice of this horizontal thing. The choice here is given to us, and then the horizontal has to satisfy this, that the tangent space breaks nicely into two, and it has this invariance property. If you go up the space, things are kind of...
Can you go back 1 second? I mean, in these slides, AT, what it is for you? The derivative in T of IT? Or
this is the
no, AT in the last line.
Here, the AT. AT is well, the horizontal space is the phi dots, right, that are allowed. And this, for us, is specified, so phi inverse is symmetric. That is the AT.
So it's the one that was solving...
This was the one that was solving phi dot is equal A phi.
Okay.
Yes, yes. And this basically amounts to the fact that as you're moving, infinitesimally you're going through little Monge maps. So stitching together Macan geodesics. So, and then here again, the picture, I'm just belaboring, trying to show the geometry behind. So you have a path up there, down there on the base space, and you start from a certain phi initial, so the phi transpose give you the point on the base space. You can lift this uniquely by solving for A this equation. This is the Lyapunov equation. So if you know sigma and sigma dot, you can compute A, and it can be given by this expression. And then you can solve this equation upstairs, and then you'll find the terminal phi at the last end. And this is the parallel transport along a curve on the base space. So you're basically traversing little steps on the horizontal direction, in a direction that doesn't make any difference to what point you're sitting, okay? This characterizes parallel transport on the fibers and gives a morphism between fibers. So you can correspond points from here to there by linking them with a curve on the base space. So, for example, if sigma loops and starts from the beginning and goes to the end, right, then you can talk about the holonomy. And the first thing that we show, which is not very difficult, it's based on the fact that if you have two, with symmetric matrices, you can find two symmetric matrices. So if you look at commutators of symmetric matrices, you only need two to generate any rotation. So then the holonomy group is in fact the whole of S O n. So in other words, any theta can be realized by a smooth curve. And then, of course, the question is, what is the shortest path? So you can show that you have complete controllability. In other words, if you specify phi in and some terminal here, it's also a consequence of the same analysis that, so if you specify these 2 points on the fiber, there's always a sigma that connects them. right? There is a horizontal curve that connects any two points on the two fibers. Okay, and this, of course, implies back that that the holonomy group is the whole of SON. And it's simply consequence of the fact that rotations can be obtained by, any rotation can be obtained by composing Monge maps. Then you can define a Sub-Riemannian metric. So up on the space, you have a metric which is the trace phi transpose some sigma ref phi dot. And this actually can be traced back to the original paper of Otto, where he showed that the Wasserstein metric is a submersion of the L2 structure on space of diffeomorphism. So this is just linear diffeomorphism. And the Sub-Riemannian distance is the minimum along paths that achieves whatever objective you have. For example, you go from phi 0 to phi 1. And it can be written explicitly in terms of the sigmas and the derivatives of the sigmas on the base space. This L over here is simply this expression. Oops, what did I do? Yes, this L here is the right-hand side of that. That if you know sigma and sigma dot, you can compute the A locally. Okay? Now, this is a very interesting expression, again, connecting to thermodynamics. Now, this is a little bit jump. You have a quantity here that basically, you see, as you're traversing from beginning to end, you're penalizing this quantity. And the interesting thing, this is quadratic in sigma dot, very much like in the Ben-Amu-Brenier formula. And this suggests that it's also connected to dissipation, because if you go very, very slowly, the derivative becomes minuscule. Okay, so there are things to connect here.
Sigma ref is whatever choice.
Sorry?
Sigma ref up there.
Sigma ref could be any choice. But in your mind, you can think of it as the identity. Maybe I should have done it like that to simplify a little bit the notation.
Does it play a role? So for every sigma ref, you have a different metric.
No, it doesn't play any role. Yes, you can take a, yes, go ahead.
No, nothing.
No, okay.
Can you
Let me
choose
see,
sigma
I have,
ref to be
yeah.
degenerate?
Say it
Can
again?
you choose sigma ref to be degenerate?
You can choose it anything.
To be degenerate.
Oh, no. We're not.
It has to be.
Here it is full rank. So then again, you can talk about isoparallel, isoparallel transport. So you have beginning and end, and you want to affect a certain transposition of particles. So this is the phi at the destination. And you have to select from the phi destination that the congruence of the initial gives you the final. And then the question is, can you find a curve, that minimal curve? And again, you can write it as an optimization problem. You can solve it. There is no closed form solution because it depends on the choice of the phi. So that the parallel transport is exactly that. And here are some pictures to exemplify the point. So here's a Gaussian, and you put tracer particles, and you can put them at various levels in the Gaussian. So, and the tracer particles traversing Macan geodesics, they go like this to their final destination. If you specify that those tracer particles go elsewhere, then there is a different isoparallel curve that affects this new transposition of particles at the end. This is very interesting because now you can also look at it as both as a control and as an estimation problem. Let's say, for example, there's fluid flowing, and I have a plume. So the plume is at the beginning, the plume at the end, and I can take snapshots and I can say something about the flow. But what if I have internal tracer particles that will resolve a little bit more rotations? So, so this kind of points in the direction that even in the classical setting, it would be very interesting to study both the transportation of densities as well as what happens to the internal structure. So here is, for example, the rotation of the base space. So the starting sigma and the ending sigma are both identities, but we specify a certain transposition of particles, and this is the optimal curve. So again, returning a little bit to the Wasserstein triangle, the holonomy of the group may not be trivial, it's exactly that, but if you choose a different curve, you can restore that, which means that by going this way, that way, and that way, you get back to the beginning. Now, here is another thing that I would like to explain. It's a building on that. So let's say you have 3 densities here. For all you know, there could be actually 3 pictures of people. Let's say I have 3 faces, okay? And normally, in computer science, they use optimal transport to relate them and sort of do a morphing from one face to another. It's also of interest to be able to register certain landmarks, for example, the eyes. So to have, for example, a distribution in the middle for which somehow you do a registration through, let's say, a Monge map or whatever, and then try to connect with now geodesics that preserve the holonomy. So when you go from here to there, to the center point and back, that this cycle has 0 holonomy. So in other words, the eyes here correspond to the eyes there and correspond to the eyes there of the registrant. And or you might want to make to morph from this to that, to that, to that, retaining again, having 0 holonomy, and trying to find what is the optimal sort of Wasserstein triangle that preserves the internal structure. So this thing here schematically shows the elements of a 2x2 sigma matrix if you follow McCann geodesics, or if you follow paths that enforce 0 holonomy with respect to a barycenter. So this could be the Aguillet-Carlier barycenter, or it could be another one. This is I forget. Which one? Yeah, an acronym of. I can bring it up later. Now I forget the name. Yes.
But I don't understand. So in the geodesics, in the black one, you don't preserve the holonomy.
So I mean, no, you preserve the holonomy everywhere.
But with the geodesics, you don't, right? You
No. You see here, let's say this is, for example, this could be a McCann geodesic. Sure. All right, and then this could be another McCann geodesic. Now you compute this curve to enforce a 0 holonomy for this little triangle.
Which is not the geodesic, then, not the Wasserstein geodesic.
This is not the Wasserstein geodesic.
But then you said in the picture there, the black was the geodesic, which means the black is not preserved.
The black is right. The black is not. Yes, the black. Right. So if you have sigma 1 has coefficients sigma 1, 1, sigma 1, 2. These are, I think, this is a 2x2 matrix, so it's specified by 3 numbers. So if you go with a McCann geodesic, this is the path they take. And those are the paths for the McCann geodesics. Now, they visit those 3 points, right? But this black triangle here has non-zero holonomy. Exactly, yes, yes. Oh, that's what you meant. Yes, absolutely, yes, yes. Yes. Now, the other one, so if you go through the red, and red, they have zero holonomy, and so does the blue, okay? And they do that by pivoting about a reference point in the middle. Yes?
Or maybe a stupid question. A zero holonomy means that let's say you fix one particle and you make sure that when it comes back,
It returns back to the
same
original
place.
position. Yes, exactly. Yes. So that is the whole point. Yes.
Like when you lift the path in the or lift the curve in the base space to the covering space, you want to make sure that the curve is closed.
The curve is closed. Yes, exactly. So now very quickly, again, I don't want to belabor this point because we don't have all that much time, but you can do more or less the same thing if the control is not the gradient of the potential and you don't have a bundle structure, you don't have a connection, and you simply broadcast all the particles again and they all follow a state feedback law like that. So you have a drift which is prescribed to you and you can do nothing about. And there is another component here which you have some control over. So provided certain conditions hold, namely that the pair A and B is what we call in controls controllable pair, there is some rank condition, then you can affect that. So the way to think about it, you have initial position of particles, you have n of them, and you're looking at n by n matrices, terminal. They have to have the same determinant. The product of determinants is positive. And you want to determine a case so that you steer it towards a terminal configuration. This is something of great application to coordinate motion and ensemble control. And basically, more or less what we want to hold holds. The proofs are not easy. So basically you have, as long as the A and the B pair satisfy a certain rank condition, there is a K that drives the state transition matrix from the starting point to any terminal over an arbitrary interval. Now, it turns out that there is no continuous choice of K that is continuous in phi 0 and phi terminal. And this has to do with the fact that SON is not simply connected. And the construction here for the K is not constructive in this setting. So it's a very delicate result. To show that you can steer the density and the base space with K, this is much easier. It's a corollary of this, but it's a much easier result. Yes, okay. And then you can do very similar things in measure orientation preserving diffeomorphisms. And there is interest for that. I'm not giving under suitable conditions, you have some control, etc. So some of this carries through, not everything. So I would like at the last part to talk a little bit about the non-commutative transport and quantum holonomy. So here, these are density matrices. And this goes back to some work by Ullmann on the Ullmann-Berry phase, what's known as that. So you have, it almost echoes what we discussed so far. So you have a curve of density matrices from beginning to an end, and the beginning could be equal to the final, or it could be something else. And again, you look at factorizations of that, of the density matrix, and recognize that, again, just as we did before, this is a gauge invariant. And then they define this quantity, which is the holonomy, and is the supremum over the U's that you can stitch together factors of the underlying curve. So you start from an underlying curve. So here, let's say, is these are Hermitian positive definite matrices. we live in a much thinner set of matrices that have trace 1. And these are the density matrices. Regardless, we can look up on fibers. So over here we have phi dagger is equal to the rho, and the rho sits down here below, rho t. And then you can have a curve here that gets you from some beginning to something else. And you can choose a gauge to minimize the angle between successive factors. So this is the trace of phi 0 star, phi next. So this is basically a cosine, right? And you try to minimize it at every little step, and you stitch them together. This is minimal if and only if the distance between successive things is minimal. You see, because you have a choice of gauge.
Tryphon, can I ask a question? So, these, I can think of them as, possible square roots of the rho.
Yes, these are square roots of the rho.
And now your fibers record the square roots,
Exactly.
not the density, or, in some other quantum information, you're looking at the set of purifications.
Yes, exactly.
A similar picture. So you're looking at fibers of purification over the state space.
Fibers of purification, yes.
And then you define, of course, the distance for
The distance there.
purification.
Yeah, this is all goes back to Ullmann.
Yeah,
Yes.
he was very good in purification, I learned.
Yes, yes, yes. So, and it turns out that optimality is the same as minimizing this quantity, which of course we recognize is nothing more than the Wasserstein length. And this Wasserstein length now runs across a curve that lives on a sphere, because the phi's satisfy the phi dagger trace equal to 1. So it's on a sphere, and that's known as the Bures length. So it's nothing more than the Wasserstein, but constrained on the sphere. The parallel transport condition is exactly what we had before, and then this is what dictates the flow of the space of the densities. So the Bures length is the Wasserstein on the sphere, tracing along this path. And there are several questions now that we're exploring, and this is some ongoing work basically, with what I told you before, you have the same principal bundle structure and the same type of Riemannian metric, a submersion onto a suitable base space. Then you can view the holonomy in terms of internal degrees of freedom or purification. And then in the classical setting, we're looking at flow with aggregate statistics and tracer particles. This is a very interesting insight. For the quantum, there are several things we're currently exploring. What is exactly the structure group? Can you realize all the holonomies? What are physically meaningful horizontal spaces? We can just play the game exactly mathematically and say a few things, but again, the connection to physics is very important. And can you specify optimal curves to get a certain holonomy? So this is, some of this work appears here, Sub-Riemannian structure of mixing and holonomy, and collective steering on GLN. And there is some more in progress with Mahmoud and Ralph. And with that, I will stop and ask for possibly some questions. Thank you for your attention.